this video, we'll be examining some physical properties of soil. We'll begin with bulk density. Bulk density is the mass of a unit volume of soil in its natural state. The volume of soil in its natural state means the volume includes not only soil particles, but also the pore spaces in soil. To determine bulk density, we need to extract a core of soil. We want to do this with the least amount of disturbance to the core as possible. To do this, we'll use a soil sampler. This one is equipped with a slide hammer. This soil sampler also has a detachable core, which can be fitted with a 200 cubic centimeter plastic sleeve for easy storage of the soil core samples. In the field, we insert the sampler into the ground using the slide hammer. We then remove the core to take back to the lab. In the lab, we pre-weigh a container. This container weighs 9 grams. After transferring our soil core to the container, we then weigh our sample. This core weighs 327 grams after we deduct the weight of the empty container. We'll want to remove the moisture from our sample to get a true weight of the soil, so we'll put the sample in a drying oven overnight. After the sample is dry, we weigh it again. The dry core weighs 285 grams after we deduct the weight of the empty container. To calculate bulk density, we use the dry weight of soil divided by the volume of the soil core. Our 200 cubic centimeter core weighed 285 grams after it was dry, giving us a bulk density of 1.42 grams per cubic centimeter. Another physical property related to bulk density is particle density. Particle density is the mass of a unit volume of soil particles. The volume of soil particles means the volume of only the solids in soil, and not the volume of pore space in soil. To eliminate the pore space in soil, and to measure only the volume of soil particles, we pour the soil into a known volume of water. Here we have 600 milliliters of water in a graduated cylinder. As we pour the soil into the water, the rise in the water level is caused by the soil particles displacing the water. The increased volume measured in our graduated cylinder is equal to the volume of the soil particles. For our example, the soil particles displaced 120 milliliters of water. 1 milliliter of water is equal to 1 cubic centimeter. To calculate particle density, we use the dry weight of the soil divided by the volume of soil particles. Our 285 grams of dried soil displaced 120 cubic centimeters of water, giving us a particle density of 2.38 grams per cubic centimeter. Once we know the bulk and particle densities of soil, we can calculate the percent pore space of a soil. Percent pore space is the percentage of void space in a given soil. This pore space may be filled with water, air, or both. Pore space allows for drainage, water storage, and space for roots. To calculate the percent pore space, we divide the bulk density by the particle density, multiply by 100, and then subtract from 100. A soil with a bulk density of 1.42 grams per cubic centimeter and a particle density of 2.38 grams per cubic centimeter would have 40% pore space. Another physical property we'll examine is particle size distribution. In order to determine the texture of a soil, we need to know the percentage of sand, silt, and clay. Sand, silt, and clay make up what is known as the fine earth fraction. In this video, we'll be determining soil size distribution using the Boyolko's hydrometer method. First, weigh 100 grams of soil and place the soil in a metal mixing cup. Then add 600 milliliters of water to the mixing cup, along with 10 milliliters of sodium hexametaphosphate. This sodium will help chemically disperse soil aggregates. Then mix the solution for 2 minutes. This will physically break down soil aggregates. After mixing, transfer the solution into a cylinder. Make sure to wash out all the coarse material at the bottom of the mixing cup. Add water until the volume in the cylinder is 1 liter. Cover the cylinder and invert it several times to be sure none of the coarse material has settled to the bottom of the cylinder. Place the cylinder on the bench top and carefully place the hydrometer into the solution. Note the hydrometer reading at 40 seconds. The hydrometer will read the mass of particles still in suspension. After 40 seconds, the sand in the solution has settled to the bottom, and the hydrometer reading indicates the silt and clay still in suspension. After 2 hours, the silt in solution has settled to the bottom, and the hydrometer reading indicates the clay in suspension. Using the 40-second and 2-hour hydrometer readings, we are able to calculate the percentage of sand, silt, and clay. The percentage of silt and clay is the 40-second reading divided by the weight of the soil used and then multiplied by 100. The percent clay is the 2-hour reading divided by the weight of the soil and then multiplied by 100. The percent of silt and clay is 13%, and the percent of clay is 3%. To determine the percent of silt, we subtract the percent of clay from the percent of silt plus clay. To determine the percent of sand, we subtract the percent of silt plus clay from 100. The percent of silt is 10%, and the percent of sand is 87%. We now know the percentages of sand, silt, and clay, and we can use the textural triangle to determine the soil texture. Using a textural triangle, we draw a line from 87% sand, then a line from 10% silt, and then another line from 3% clay. The soil texture is sand.